Hello, and thank you for joining us. Today's webinar is Laser Ablation 201, Applications of Laser Ablation and Data Reduction Strategies. Our presenter is Dr. Cyprian Strempton, Global Product Specialist, Laser Ablation. We will be taking questions, so feel free to submit your questions throughout the presentation using the question feature, and we will address them at the end. Also, this webinar is being recorded and will be available for viewing within a couple of days. You will receive an email notification of its availability. Okay, I will turn it over to our presenter, Dr. Cyprian Strempton.
Hello, everyone, and thank you all for joining us today for the third webinar of Teledyne's Laser Ablation series. The webinar is titled The Applications of Laser Ablation and Data Reduction Strategies. I want to thank everyone for joining, and especially for those who are logging in early in the morning their time or late in the evening. And I'll try and keep it as short as possible. So you can either get back to finishing your coffee or wrapping up for the day. Now, my name is Cyprian Strempton, and I'm Global Product Specialist for the laser ablation products at Teledyne Photon Machines. My background is in mineralogy and geochemistry, or geology rather, and with a PhD in geochemistry. I've been lucky enough to work with lasers and laser ablations for more than 12 years now. And to be honest, I'm really happy that I had this great opportunity to work with teams from various fields of research, anywhere from earth sciences, with that being my background, to archaeology, archaeometry, material sciences, life sciences, and so on and so forth. And throughout those 12 years, it was always amazing to me, and still is, to be honest, to see how a technique which was initially developed, for geochemists and earth sciences in general, made its way into so many fields of research. Now, hopefully, most of you have already seen parts 1 and 2 of the webinar series presented by my colleagues Lucas Smith and Damon Green. Lucas is our Director for Business Development for the Americas, whereas Damon is the VP of Technology. Or if you haven't, I strongly recommend taking a couple of minutes, maybe today, tomorrow, and watch them. They're available on our website and also on YouTube. And hopefully, if you haven't seen those webinars, you are already kind of familiar with some of the key concepts presented by both Lucas and Damon. And I'm talking about, the choice of wavelengths in laser ablation, the pulse width, the ongoing work between nanosecond lasers, femtosecond lasers, and so on and so forth, the choice of carrier gas, the washout speeds, and so on and so forth. So I will not dwell too much on them, but what I would rather do is focus on how they impact the applications and the data reduction side of things. Now, the structure of today's webinar is pretty straightforward, and we'll just start with a few general remarks regarding the most common applications for laser ablation ICP-MS, as well as analytical strategies, and then we'll dive right into fast elemental imaging. Now, fast elemental imaging, or elemental imaging in general, is quickly becoming more and more popular, and not only in earth sciences, but in medical sciences, biological sciences, and so on and so forth. And by looking at the fundamentals of imaging and the application in general, I'll show you how to use Photon Machines HTIP software to design the imaging experiments. So start from scratch, basically, and then generate the image, and then work with the data sets once that data is acquired. As I mentioned a little bit earlier, laser ablation was initially developed for earth scientists, And thusly, people were looking mostly at bulk analysis back in the days, so major, minor trace elements. But since the analytical technology has developed dramatically the last tens of years, isotope ratio, mass spectrometer, both stable isotopes and radiogenic isotopes, and temporal introduction for those techniques via laser ablation has also become ubiquitous. Now, it's not uncommon to find laser ablation instruments in labs anywhere from earth sciences to forensic labs, archaeology, archaeometry, and everything that has to do with quality control. Pharmaceutical industry, metals, alloys, material sciences, but also, and increasingly more so, I would say, in biological labs and in medical research facilities. And pretty much anything else that has to do with the analysis of solid samples. Now, laser ablation has been around for a while now, so it's a fairly mature technique. So let's see what options are there when designing an experiment, irrespective of the area of research, and how designing that experiment dictates, or the mindset behind it dictates some of the acquisition parameters, both on the laser side and on the ICP side, because that's actually very important. Each application requires a certain analytical approach. And one of the biggest advantages of laser ablation ICP-MS techniques is their spatial resolution. In other words, with the same system, you can do 1 micron spot size single spot analysis, but you can also do 200 microns line scans and so on and so forth. If you think about it, this technique allows you to run multi-dimensional spatial analysis. So from single spots to the analysis of volume, so basically 3D reconstructions of solid samples, which is pretty neat, and hopefully we'll have some time to show you some of those examples as well. Now, initially, laser ablation, or when it was initially designed and the first instruments, they were used mostly for single spot analysis. And single spot analysis still is the typical analysis in laser ablation ICP-MS labs. If you think about it, when the technique was designed and invented, it was a huge step forward from people digesting whole rock powders or mineral separates, so techniques which are really time and resource consuming. And in this case, single spot analysis saved a lot of time, saved a lot of resources, and so on and so forth. But not only single spot analysis. Now, line scans are another tool used in laser ablation ICP-MS in terms of generating the signal. And they're actually very versatile tools, because you can use them for bulk analysis. You can like you've seen on the left-hand side in the video, you can raster an area, so you're collecting more sample. So we're increasing the sample yield to the ICP's plasma. But if you think about it, when you stack those lines, you're creating actually an area, and this is where things start to be really, really important and interesting, especially from an imaging point of view. Because, like I mentioned, you can generate profiles along surfaces, and then when you stack those profiles vertically, you can get 3D reconstructions. So you're basically generating layers after layers and then putting everything together into a volume. Now, the reason why I'm showing this image on the right-hand side, and for those of you who've seen the previous webinars, you're probably familiar with it. So this is a garnet that we've analyzed using a time-of-flight ICP-MS from TOFER and one of our lasers. So the idea behind it was to compare this imaging technique with a more seasoned, so to speak, imaging technique, which was microprobe analysis. So we wanted to look at resolution and we wanted to look at acquisition time. So the same sample was analyzed using a microprobe, and then the coating was removed, and we ablated that and measured the distribution of certain elements. And the huge advantage of this technique, aside from the spatial resolution, is that it took only 48 minutes to generate these maps. Whereas with the microprobe, it took us, I can't remember exactly, it was anywhere between 12 and 14 hours. So you gain a lot of speed, and the sample throughput increases dramatically when you're using laser ablation ICP-MS. Now, I mentioned imaging, right? And a couple of examples in the previous slide. So why is imaging so important, and why is it getting more and more traction in the research world? Well, to be honest, and if you ask any physician, they will tell you that the human eye is trained, so to speak, to recognize patterns. If you think about it, what's easier for you to understand? The image on the right-hand side, or the numbers, the matrix on the left-hand side? Essentially, the data is exactly the same, just the way in which it is represented is different. So what we're seeing on the right-hand side is the distribution of uranium in a zircon from the Eastern Carpathians of Romania. The image was generated on a quad, so the data was acquired on a quadruple ICP-MS instrument, and the image was generated using HDIP. On the left-hand side, we have the numerical data for the same analysis, or a chunk of it. It's not all of it. And that is to say, the numerical values for the uranium signal for each individual pixel comprising the image on the right-hand side. So which is easier to understand? For me, the one on the right-hand side makes more sense because I can easily spot differences. I can see growth zones, I can see patterns, and I can get a rough idea of what happened with that particular sample. Whereas on the left-hand side is not as evident. Of course, you can use software to get a rough idea about what those numbers mean, but it's not as evident as the image on the right-hand side. So what's the process for getting to this image? So how do we get there? What are the stages that a user needs to go through, the steps rather, to go from a sample, so a couple of mineral mounds or a tissue or something that's planning on analyzing, so the user is planning on analyzing them, how to get from that to the image on the right-hand side, and what's the approach, what's the mindset, so to speak. Well, it all starts with the fundamentals, really. And when I'm talking about fundamentals, I'm talking about understanding how the acquisition parameters, both on the laser side and on the ICP side, interact with each other and how they impact the quality of the final data. Now, a lot of work has been done over the years, and especially in the last, I would say, 5 to 10 years, looking at the fundamental concepts of imaging. And what you see on the screen right now is by no means a comprehensive selection of scientific papers dealing with imaging. And you have pretty much a little bit of everything from hardware developments to software developments to understanding the math that governs modeling the imaging parameters and so on and so forth. Now, keep in mind though that having a capable hardware like, I don't know, fast aerosol transport devices or fast washout cell high repetition rate lasers, devices that, or lasers rather, that can ablate spots smaller than 1 micron, does not always translate into having good quality data. It's not just pushing a button on the left-hand side and getting, a pristine image on the right-hand side. We're not there yet, but we're getting there. So, but definitely having capable hardware helps, because it makes everything easier when you're designing an experiment. Now, understanding the acquisition parameters for an experiment, for an imaging experiment rather, and knowing what to choose to get the best resolution, the best signal to noise ratio, reduce the number of artifacts, if possible, for a particular sample, being a mineral or a tissue, and so on and so forth. It's actually critical, and especially for people or labs working with valuable samples that require non-trivial sample preparation techniques, that it's even more important. And I think here is where HDIP, or the Teledyne's software for doing data reduction, but I'll show you it's not only for data reduction. Here's where this software comes into play. Now, for those of you who don't know, HDIP was developed at University of Ghent in Belgium by Dr. Steen van Molderen and Dr. Frank van Hake's group. HDIP really started as a PhD project, but evolved quite nicely into a complete, really complex and extremely useful piece of software. And the nice part of it is that it is continuously evolving, which with each new version you have more and more features added. And even I did say that we're not there yet when we're talking about pushing a button on the left-hand side to get the sample, and then to ablate the sample rather, and then getting the numbers on the other side. We're actually getting close to be there. Now, I would definitely not have enough time to go through all the features available in HDIP. So I strongly recommend getting in touch with us if you have any questions, or if you think that you or your lab or your application of interest will benefit from having a more in-depth discussion about HDIP's capabilities. And towards the end of the slide, I'll provide you with email addresses and so on and so forth for doing that. Before getting there, though, in the following slides, I will show you a couple of screen captures, a couple of videos rather, showing some of the basic functionalities in HDIP related to imaging applications. And when I'm talking about basic functionalities, I'm talking about, for instance, calculating the peak statistics so that you know, or the single pulse response of the system, so that you know or have a really good understanding of the washout or the speed of your system. Also, I'll show you how to model the imaging parameters so that you increase the quality of the data, so you know exactly what parameters to use, both on the laser and on the ICP side, excuse me, to minimize the downtime. And also, I'll show you how to generate the actual images based on the ICP data, the raw data from the ICP, and the log file, the spatial data from the laser ablation system. Hopefully, if we'll have the time, I'll also show you some basic operations with the image data. I'll show you how to manipulate the data, how to change colors, and so on and so forth. Okay, so one of HDIP's key features is the ability to describe the performance of the system. And it didn't start. There you go. So the so-called single pulse response. And that's actually very important, because the single pulse response is one of the pillars for modeling the acquisition parameters. And what you see here on the screen is the main interface of HDIP. And we've loaded a data file. We've ablated, I can't remember exactly what, a natural sample, so it's inherently heterogeneous, but it was really nice polished, and we were looking at calculating the washout time. So we ablated a couple of shots, I think about 100 and something shots, and then loaded that data into HTIP. And what we'll do now is we'll check the signal processing capabilities. Now, when you are trying to get the peak statistics and try to calculate the washout, HAP offers you a ton of parameters for peak detection and for filtering the signal before running the peak detection algorithm and so on and so forth. HAP is really good at automating things, and it's also really, really good in allowing users to tinker with every single parameter that can be adjusted. So what I'll show you now is just an automated procedure for calculating or getting the peak statistics to calculate the single pulse response of your system. So here on the left-hand side, we'll have the parameters for the peak detection algorithm, some of the parameters for filtering the signal, and then the numbers, the peak statistics on the right-hand side. Once you're happy with that, and if you feel that you need to fiddle with those a little bit more, then the peak statistic tab actually runs the algorithm and gives you the numbers. And what you can do here is decide the width of the peak that you're looking at, 10%, 1%, and so on and so forth. And in the background, the software will do the calculation for you. And you can see it takes each individual peak and runs the algorithm on it. And then when everything's finished, you'll get the numbers plotted on the right-hand side together with the peak profile for your data set. And this is actually quite important because you can actually export this data as a CSV file, or you can store it and use it later for running the optimization algorithm. And this is basically what I'll show you in the next slide. Once the import parameters are saved, either as an Excel file, like I said, a CSV, or you can even write them in your logbook, lab book, or anything, or save them as part of your experiment file. The next step in designing the experiment would be to model the acquisition parameters. And for that, HTIP requires a couple of data sets, actually only one data set, and that is one line ablated on your material of interest. Now, it doesn't require any spatial data from the laser for this particular type of analysis. So what you need to do is ablate a line, load that data into HTIP, and then it will run the optimization algorithm for you. It's actually a two-step process, and I'll walk you through it. Initially, when you first install HTIP, it will ask you a couple of the hardware parameters, or the parameters of the hardware that you have in your lab, both on the laser side, so the maximum, the minimum repetition rate, the scanning speed, and so on and so forth. And also the some of the parameters on the ICP side, the dwell time, and so on and so forth. Once you have that, the next step would be to train the algorithm, or select rather a blank region and one of your sample. And then based on the parameters that you choose to be optimized for the image, be it a certain signal to noise ratio or spatial resolution, it will do these calculations in the background. So like I said, the first step for now is to select a region for the blank signal and then a region for the sample itself. And you'll see that it's actually pretty straightforward, because when you're selecting the blank or the sample, it automatically drops a shaded area, so to speak, on your signal, or on your data rather, and then you can manually drag and drop it and extend it, shrink it, so that you cover as much blank or as much sample as needed for the experiment. And you can see in the video, it's pretty straightforward to use. You just need to drag it, select the width or the time slice rather. and once you're happy with your selection, you just click on select the region either for the blank or for the sample. Once you're done with that, you're going to go to the next step, which is the acquisition settings. So basically, HJP is asking you, okay, now tell me what parameters you used for acquiring that particular data. And that's the dwell time for each individual masses that you've analyzed, the overlay, not the overlay, sorry, the overlap, so the dosage basically. It also needs the parameter that we just calculated in the previous step, so the single pulse response, and also the repetition rate at which the laser fired. And once you're happy with all that, once you're happy with the dwell time and the parameters, you just click on calculate, and the laser will calculate, the software will calculate the optimized parameters, both the dwell times and so on the ICP side, as well as the scanning speed and the spot size to meet the criteria that you've initially input. In this particular case, a signal to noise ratio of more than 10. Now, I actually made a mistake when I ran those samples, because the well, not a mistake per se, but the washout was really fast. So it was about 3 milliseconds, actually slightly faster than that. In which case, to maximize the signal to noise ratio, the laser will need to go faster than the maximum repetition rate of the laser that was that the laser ablation was equipped with. In other words, so you can see here, HJP gave me a warning message saying that, you know, you might actually you'll need to go too far, a little bit faster in order to get the results that you want. But you can go back and rerun those analyses and correct for any mistakes that you've made. And once you're happy with the results, on the right-hand side, it actually gives you an image preview of how the data will look like on a resolution target. So it gives you a rough idea if you're going to get any signal, noise, or aliasing, or things like that. So pretty straightforward to use, and it will definitely let you know if you're making any mistakes, because you'll have all sorts of warning messages popping up throughout your modeling procedure, or optimization procedure rather. Now, we have all the data we need in terms of optimizing and knowing what parameters to use. Let's assume we ran the experiment and we have the data from the ICP and from the laser. So the next step will basically be constructing the image. Now, in order to construct an image, you'll need to generate a project file. And HJP uses HTF5 or H5 files, which are really good for storing large amounts of data, but also for storing different types of data within the same container. Once a project file is saved, the next step would be to choose the technique, select the data, and you're good to go. Now, by default, HJP assumes that you want to do laser ablation work. So the technique, the default technique will be laser ablation ICP-MS. Then the next step would be to select the data that you want to use for your image reconstruction. Now, HJP comes with a pretty comprehensive libraries of data formats from all the major manufacturers for ICP-MS instruments. And it also comes with a really powerful algorithm for automatically recognizing the type of data that you're using. So, in other words, when you're loading the data, you can either select the type of instrument that you've used from the drop-down menu, or just set it to auto, and the algorithm will look at the metadata and the syntax and decide what import procedure to use. And it's the same for the time unit and the signal unit. You can either manually select it, or based on the data that you're loading, it will do that automatically. Now, depending on how you've designed the experiment, either if you have it as your imaging experiment, everything saved as one file, or each individual line saved as a different file within a folder, HAP can load that. So either a single file or an entire folder. For this particular experiment, we've saved everything as one single file. So when you're importing the data from the ICP-MS, immediately you'll see the selection of mesh channels that you've analyzed or monitored rather, and you can select all of them, none of them, a handful of them, depending on what you want to do with the data. It also imports and calculates all the important data, the acquisition parameters from the ICP. You can still edit those. You can still edit the dwell times manually, and that's actually quite important to have the exact dwell times, because that will impact the image reconstruction quality afterwards. When you're happy with this selection, the next step would be to import the laser log file. And it's the way in which the laser log file is designed and the way in which HTAP is designed to look at the laser log file allows it to automatically recognize sample types. In other words, if you ablate a NIST glass, for example, like in this case, a 612, and you name it a NIST, 612, 610, whatever, in your scan list, HTAP will recognize it as being a standard reference material, and because it comes with a good chunk of the GRM database built into it, it will automatically recognize it and it will link it to the database. So you see that it automatically says, well, this is a NIST 612. I'm going to use the GRM database because that name popped up in the GRM database that I have with me, and then the reference values for that particular standard. Now, keep in mind that because HTAP can run really complex procedures for generating images and working with ICP data, you have a number of options or a number of sample types available. Calibration standards like this particular NIST. You have primary, secondary standards. You have sensitivity drift, quality control samples. You have interference standards. You can even load background, blank files basically, and it allows you to import procedural blanks, which is a huge advantage for some applications. And it's also worth noting that even though HTAP comes with, like I said, a good chunk of the GRM database built into it, you can still build your own as a user. You can still build your own database for standard reference materials. Let's say you work in a lab and you're using, excuse me, a number of in-house standards which are not available on GRM. You can generate your own database for those standards and use them in your analysis. And HTAP comes with a really neat tool for generating and working with databases for standard reference materials. So we pretty much have all the data we need now to generate an image. So we have the ICP data, we have a rough idea on the acquisition parameters, and we have the spatial data from the laser. So now we have two options to generate the image. We can either use an autopilot function like a processing pipeline, which is works on a build your own kind of a thing, and it's automated, or you can do everything step by step and control each individual part of the process. And I'll show you the latter. So I'll show you how HTAP takes into account some of the issues that crop out from not having the ICP synchronized or the clock synchronized with the laser PC and so on and so forth. But keep in mind that the same procedures are running in the background when you're doing the autopilot. Okay, so the first step, once you've loaded the data, is to make sure that there's no offset or no time shift between the data from the ICP and the data from the laser side. Now, there's a bunch of ways for doing that, either manually or automatically. Because having completely synchronized data is so important, especially when you're doing high resolution work, HTIP allows the user to control the time offset or adjust for the time offset really, really fine. So you can do fine adjustment and rough adjustment either manually, or it does have a powerful set of algorithms which can account and compensate for those differences in synchro or that time offset. And also for systems, for lasers who are capable of doing bidirectional ablation. So you're ablating one line left, right, and the following line right, left, and so on and so forth. It can also correct for that. So it does have a bidirectional shift correction algorithm built into it. Once you're happy with with what you're getting in terms of synchronization, the next step is to do the background correction. And again, because you have access to a plethora of parameters, it's usually easier just to run the automated procedure. But if you don't want to do that, if you want to control each individual step, you can do that. So when you're fitting the background model, so to speak, you can do that either looking at the total mesh channel or each individual channels separately. And you can save the fitting details either as a CSV file or just copy them on the clipboard, because that's actually quite important for some people and for some labs. And you can also modify the regions at which HTIP looks at for establishing the blank. So it allows you to run quite a few things manually, so to speak, and finally control all these parameters. Now, when you're okay with that, when the operator is okay with that, the final step is the actual reconstruction of the image. Now, I want to make a really important point here, and this is one of the features that stands out in HTIP, is that, well, most of the data reduction software that do have this ability to generate, images or work with image data, they use fairly simple algorithms for generating an image or for reconstructing an image. Now that is, the general consensus is that, well, the first pixel of each line is a line either on the left or on the right side, depending on the direction of scan. And then it's assumed that the velocity of the stages is constant, right? So it means that each pixels will be evenly distributed throughout the line, basically in terms of speed. Now, there are multiple issues with this approach and with this assumption. And the most important is that the stages, and it doesn't really matter how, if they're high resolution or, really, really, fine return accuracy and so on and so forth. Each individual stage will have an acceleration and deceleration curve. And if you don't take that into account, then you might have some issues with the quality of the data when you're reconstructing the images. Now, HTIP comes with 5 different algorithms to reconstruct the image, and all those algorithms take into account and try to mathematically compensate for this acceleration and deceleration curve. And this is actually very, very important, and it's an important point to make. So we're happy with the data, we're happy with the selection, and that's pretty much it. That's how you generate an image. And it actually takes less time to generate an image than it took me to explain how to do it. And it's even faster when you're doing it automatically, so using the autopilot feature. Once you've generated the image, and in this particular case, we're looking at the garnet. We only measured or we only monitored a handful of elements. And once the image is generated, you can scroll through these elements, or masses rather, or channels, and select the ones that you want to visualize. Once you're happy with that, you can then, you have access to a number of options to improve the quality of the image, change the scale, change the color scheme, work with the transparency, and so on and so forth, use inverted colors. So it does allow you, once you've generated the image, to do quite a bit of work to improve the quality of the image. And this is actually quite important because it does that without fiddling or massaging with the numbers afterwards, which is very, very important, especially for quality control labs and so on and so forth. Once you're happy with how the image looks like, you're happy with the contrast and so on and so forth, the next step would be to run the standard. So fully calibrate the sample if you want. And because we analyzed one NIST glass, it's usually, single point calibration curves are not the best in the world, but for the purpose of this webinar, I'll just show you how to use it, or how to use the external calibration procedure to fully calibrate the samples. So what goes, the video on the screen now shows you how the calibration curve is created, and for each individual sample, for each individual channel, once you're happy with the curve, you can just apply the calibration and then you're done. When you're applying the calibration, or before applying the calibration rather, you can save the reference set for later use. You can go back to it and you can open it and then see the results and export the numbers and so on. So once you've created and exported, or saved rather, the calibration data, then it's just a matter of choosing which data set you want to calibrate, and then just perform the calibration. And once you're done, once you click on perform calibration and the calibration was successful, you get this successful calibration message, and then you're done and you're ready. You're ready for the next step, basically, which is working with the data sets or the images that you've created. And for that, I've selected a data set that was generated using a time-of-flight instrument. It's still a rock sample. This is from it comes from a bonanite. The sample was kindly provided by Dr. Jeff Ryan, and from the University of South Florida, and John Chavez from Utah State. But like I said in the beginning, the procedure is exactly the same for biological samples as well. So in this particular case, we've measured, or we've analyzed the sample using a time-of-flight instrument from TOFER. And if you have one of these instruments in the lab, a time-of-flight instrument, it doesn't really matter if it's a TOFER or a new instruments we test. HTAP comes with a built-in data processor that can handle both data formats, and it can process those files. So in order to do that, you just select the type of data that you want to import. In our case, it was a TOFER or ICP TOF image file. Import it, select the algorithm that you want to use to convert the data, and you're good to go. The software HTAP will convert the image in the background, and in the end you'll have completely or fully compatible H5 file that will work in HTAP. So once you've imported the data, you're good to go. So what I'm going to show you in the next couple of minutes is how to visualize the data. So jump between different elements or channels, so to speak. I'll show you how to generate transects through the images that you've just created, excuse me. Extract that data. Also visualize and extract regions of interest, which is really important feature, especially for geologists, but not only for geologists. And also run some basic math operations with the channels, create some composite images, and of course, export your data. Now, because the data set was acquired using a time of flight, you have access to a huge amount of data. So this particular data set is about, I think, 2 gigabytes. So you have a lot of data that comes with it. So when you're scrolling or when you're changing from one element to another, you have a number of ways, or visualizing the data rather, you have a number of ways of doing that. Either the scroll, the drop-down menu that you've seen, or you have this option of having a periodic table available, and all the elements that you've analyzed are highlighted. And when you click on one of those elements, and if you have multiple isotopes of that particular element analyzed, they're listed on the right-hand side of the panel, which is quite useful to have, especially when you work with large data sets like time-of-flight data. We also have this spatial overview of the data feature, which allows you to visualize, like thumbnail style, all the images that you've generated within the data set. And you can scroll through them, you can zoom in, you can zoom out, and so on and so forth. Okay, so this looks pretty straightforward. So once you're happy with how your data looks like, the next step would be, just run some basic, or show you how to run some basic procedures using HTIP. And the first one would be how to generate and extract a path. So a transect basically through your data. And it's straightforward to do. You literally just draw a line on your image of interest. And then once you're doing that, HTIP will automatically extract that data and plot it for you. So in this case, we're looking at iron 56, I think, right? And you can see the ground mass is pretty monotonous. There's not much in it, but once you jump over that particular grain boundary, you have that spike in signal. Now, initially, the width of the path, so to speak, is 1 pixel, but you can easily change that. You can just click on the middle of it and just scroll up and down, and it changes the resolution. And you can also change the endpoints of your line. So right now, you see that the path goes from one grain to another. So you see that 2 large peaks at the grain boundaries, and then not a lot of signal for the ground mass. And you can also overlay multiple channels basically. So right now we're looking at iron, which is red, and then magnesium, kind of green, and I think aluminum, kind of brownish in color. And when you're happy with the selection of channels, you can save the data. You can either save it as an image, like a PNG, excuse me, or as a CSV file. And you can work with it afterwards in Excel or your choice of software. The next thing would be to show you how to extract and visualize regions of interest. It's pretty straightforward to do it. Initially, or the easiest tool for that is the flood tool. So once you've enabled this tool and the flood tool is selected, you just click on a pixel, and then the algorithm will look at all the adjacent pixels and cluster them together. And of course, you can change the flood tolerance, so you can play with that a little bit as well. And every time you select or generate a region of interest, you can save it. And you can save it and work with it afterwards. You have a number of tools available, excuse me, for saving or generating rather regions of interest, either drawing squares, ellipses, freehand drawing of polygons, and so on and so forth. And once you're happy with the area that you've selected, you can save it, you can rename it, and so on and so forth. It does have a number of other automated tools available for the region of interest, and I'll show you in a couple of seconds how to do that. But you can see it's actually pretty powerful in picking up regions of interest. So in this particular case, just looking at iron 56, I think it was, you can see all these, or the zonation, the rim, the high concentration, the high intensity rim, it picked it up really, really nicely. Like I said, you can rename it and save those afterwards, either as CSV files or within the H5 project file. A really neat feature of the of the region of interest tool is that it allows you to cluster the data based on a couple of algorithms. So if you're assuming that you have, let's say, probably in this particular case, I was assuming 5 main clusters or 5 main groups of concentrations or intensities, you can do that, and you can just generate the clusters, or it can generate the clusters in the background based on the information it received from you. And as you can see, it's actually really powerful, and it can do a lot of things, and the accuracy with which it picks up regions of interest and zonations is outstanding. Another option for the region of interest tool is to run your own filter, basically based on logical operators. So if you know that one of your region or one of your mineral grains or a slice of your tissue has, let's say more than 5 ppm aluminum and less than 10 ppm magnesium, you can manually input that, and it will look at all the pixels and group together all those pixels that fit that criteria. Okay, so the next step would be, in this particular case, or for this presentation, would be to show you how to do some basic signal processing procedures, and how to do or how to work with channels, how to calculate ratios, sums, and so on and so forth. Actually, the algorithm behind it, it's really powerful. So if you're familiar with the syntax, you can do pretty powerful stuff. But for this, we're just doing a simple ratio of 2 channels. And HTIP allows you to automate some of these things. So you can save a set of operations and then load it afterwards. And it's exactly what I've done here. So I saved a number of those operations, and then I've loaded those or opened those operation sets. And right now we're going to look at how the ratio of nickel to chromium looks like for this particular sample. So once you're all set with describing the operation, you can click on apply or on OK, and it will generate a new layer, so to speak, for your image. And then you'll need to scroll down to the very bottom of your drop-down menu, and here you are. This is how your nickel to chromium ratio looks like for this sample. And like I said, it can do a lot of powerful stuff if you're familiar, or when you become familiar with the syntax for the math operations. And of course, when you've created such a layer, a ratio or a sum or a multiplication, you still have that option of using all the other tools. You can change the scale, you can change the color scheme, you can generate regions of interest, and so on and so forth. And the last feature that I'm going to show you is how to generate composite images. So basically, how to plot multiple channels on top of each other. So right now we're looking at sodium, titanium, and I think it's lead, right? So it allows you to overlay a number of channels to create composite images, which in the end, beside the fact that they can look stunning, from an aesthetics point of view, they can they do offer a lot of information packed into one single image. And the very last thing is to generate the image itself, or to save it rather. And when you do that, you can save it as either as like a PNG file for publications. You can save it as a raw file. You can save it as a CSV, and so on and so forth. So in a nutshell, this is basically how to use HTIP for imaging processing, and start from scratch. Get the single pulse response and see how fast your hardware is, and then based on that, model the optimized parameters for imaging, use those parameters to run the experiment, save the data, generate the images, process the images, work with them a little bit, and then save the final product, so to speak, which is the image in itself. That's pretty much it in terms of showing you the capabilities and talking about the applications for this webinar. Now, keep in mind that HAP is a pretty complex piece of software, and there's no time in half an hour or 45 minutes to go through all the features. However, if you want more information, we have a website dedicated to HTIP, and there's also the user forum, which is growing exponentially, and where you can ask questions, get support, and so on and so forth. So you're more than welcome to visit our website and get more complete documentation and see how the features look like, and what the benefits of using HTIP are. And with that, I thank you for your attention. And if you have any question, I'll be more than happy to reply. And if you have any questions regarding the previous webinars, the one hosted by Lucas, by Damon, you're more than welcome to email us directly, and we'll try and make sure and reply to your questions as soon as I can. And with that, again, thank you so much. And we are open for questions. Just 1 second. Oh, there's quite a few of them. Now, unfortunately, I don't think we'll have enough time to run through all of them. So I'll pick a handful of them, try and reply them as quickly as I can, and then I'll try and send you a more detailed reply personally via email. Okay, so right. Can HTIP handle single spot analysis like bulk analysis, trace elemental data, and so on and so forth? That is a very good question, and yes, it can. It actually has a dedicated module for doing bulk analysis. Unfortunately, there's not enough time now to do that, but it can. So it can do bulk analysis, it can do major, minor, trace elemental concentration or work. It also has an at this point limited amount of isotope ratio data reduction schemes built into it, but we're working on that, and we're getting better and better with each release. So yeah, in a nutshell, HTIP can do bulk analysis not only, or single spot analysis, not only imaging. The next question, will HTIP work with Teledyne with CETAC lasers only? Yes, for the time being, yes. So the algorithms, especially the spatial reconstruction algorithms, are designed and constructed around the laser log file generated by the CETAC or photon machine lasers. Unfortunately, for the moment, we're focusing on that, and just because we're trying to polish all the rough edges in generating images and to make it or make the process rather as smooth as possible, we're only working with log files from our lasers. So for the time being, HTIP will only work with data from Teledyne or CETAC lasers. All right, another question. What is the relationship between HTIP and chromium? Can HTIP be used with other laser systems other than Iridia? Yes. So the short question is yes, HTIP can be used with all the laser ablation systems manufactured by CETAC or photon machines. So I'm talking about 213 lasers, excimer lasers, the entire range, so Excite, Excite Plus, HE, and Iridia as well. It can also work with femto data, so data generated by the Ferrous system. So basically, everything, all the platforms, all the lasers within CETAC's portfolio that use Chromium as an operating software and can do laser ablation, that data output can be imported and you can work with it in HDIP. Another question, do you know how long the data for the Bonanite map took to collect? That's a very good question. I was actually, so before the webinar, I looked, I was trying to find the original data, the raw files, but I couldn't find them. So I cannot give you, you know, an 100% accurate answer, but I'm assuming in between, I want to say 1.5 and 2 hours, something like that. And it looks like the questions keep coming in. So we have time for one additional question. And like I said, for all the other questions that were asked, I'll try and I will try rather to reply as soon as possible. Hold on, where was that question? Hold on, I think I just minimized the window, so bear with me for a second. Right, there we go. So what about the use of internal standards in quantification? Yes, so you can, that's actually a very good question, and that kind of applies to the first question that was asked as well. So there's several ways of doing standardization or calibration in HDIP, including including using internal standards. And that works for maps, and that works for single spot analysis. Now, there was not enough time to go through how to do that during today's webinar, but HDIP's documentation, which hopefully is available on our website, gives you a pretty detailed description on how both the external and internal calibration work. But you know, to answer shortly to that question, yes, you can use internal standards as well as external standards for calibrating your samples in or using HDIP. And with that, I want to thank everyone again for attending our webinar series. I want to thank you for all the questions that you've asked, and by the looks of it, they're still pouring in. And if you have any other questions regarding Lucas's or Damon's webinar, please get in touch with us. You have the email addresses in front of you on the slide, and we'll be in touch. So thank you everyone again, and have a good day. Bye.